This is the pre-lab talk for Chem 120's experiment number 12, rates of reaction. The major goal for this experiment is to allow you to explore the kinetics of an iodine clock reaction. There are 4 parts to this experiment. In the first part, we'll just take a look at the reaction itself, and we'll also look at the effect of sodium thiosulfate as an iodine scavenger. Then in part 2, we'll determine the rate law for the reaction. This means we'll determine the order with respect to each reactant and the rate constant at room temperature for our iodine clock reaction. In the third part of this experiment, we'll briefly look at the effect of 2 catalysts on the rate of our iodine clock reaction. And then finally, we'll take a look at the effects of temperature on the rate of reaction by running our clock reaction at a lower temperature than room temperature. We'll calculate a new rate constant and use this to get an activation energy for the reaction. Here's our safety pause for today's experiment. Fortunately, there are no specific safety warnings for this experiment. All the reagents are safe or have low hazard associated with them and can be safely rinsed down the drain with plenty of running water. However, in all experiments, we do want to make sure we wear our lab coats and our safety goggles. What is an iodine clock reaction? Well, clock reaction is where we mix together several reagents that form a complicated reaction system that are colorless in solution. And in a very easy to measure specific amount of time, we get a color change as products are formed. Iodine is typically used in clock reactions because I- is colorless in solution, and elemental iodine, I2, is a brownish yellow color in solution. There are several forms of the iodine clock reaction, which you can confirm by doing a simple Google search. However, this is the version we're going to use because the reagents hold pretty low risk associated with them. The net ionic equation for the reaction is between 2I- and the persulfate ion, S2O8, 2-, to form elemental iodine in solution and 2 sulfate ions. Now I mentioned that I2 is a yellowish-brown color in solution. However, since we'll be timing this reaction, we want a very sharp color change, which is not provided by just looking at plain iodine in solution. So we're going to use an iodine indicator. And the most common one, guys, is used is the starch solution. You might have used starch to detect potassium in potatoes, or actually you use iodine to react with the starch in potatoes. In a biology class in high school or middle school. So this is the same principle. Iodine will react with the starch solution to form a bluish-black color. Now, in order to get the rate of reaction, we do need a very clear way to look at the change of concentration over a time interval, the time that it takes for the solution to change color. To do that, we're going to use a scavenger, which in this case will be the thiosulfate ion. Thiosulfate reacts with elemental iodine in solution to form 2I- and S4O6, 2-. Now, what does it mean to be a scavenger? So the thiosulfate ion, if we add it into the solution with the first reaction, what will happen is, as iodine is formed, the thiosulfate will immediately react with that iodine to form 2I-, keeping the solution colorless. If we add a known amount of thiosulfate, we'll know that when the solution changes color again is when the thiosulfate actually runs out. Since we know specifically how much thiosulfate we added to the solution, this gives us a means to calculate the rate of reaction. So here are some equations for you. So we know that we're measuring the rate of reaction by looking at the appearance of iodine over some time interval. We can use the relationships between the rates of reaction to also see that this is equal to 1/2 the change in concentration of thiosulfate over the time interval for the color change. We know that when the color changes, all of the thiosulfate has disappeared. Therefore, we use the concentration of thiosulfate to calculate our rate of reaction for all parts of this experiment, especially in part B, where the concentration of thiosulfate is held constant. This equation, that the rate is equal to 1/2 concentration of thiosulfate over the time, is equation 8 in your procedure. It is really important that you use equation 8 to do all calculations. Here's some points about the procedure for this reaction as you watch the videos. First of all, it is very important that we keep all of the glassware clean. This is because, as you'll see in part 3, when you observe the effect of catalysts, we don't want the presence of other ions to interfere with the reaction itself. All glassware is scrupulously cleaned before running this experiment. You also notice that we're using graduated cylinders to measure our reagents. When we use graduated cylinders, we're carefully measuring the volumes specifically to the marks on a graduated cylinder and adding to determine the amounts of reagents used. For this experiment, we need consistency and not necessarily a high amount of accuracy. This can be accomplished by using graduated cylinders. We're also going to be careful about how we add the reagents. And this is very important because we're dealing with a lot of colorless solutions. All reagents were labeled in this experiment, and we were very careful to prepare a solution so that we start with a mixture of potassium iodide, sodium thiosulfate, and starch solution, and then added the potassium persulfate to start the reaction. So we have Ki, sodium thiosulfate, water, and the starch solution in our 250 milliliter beaker, and we add potassium persulfate to start. The analysis for this experiment can be pretty involved. So here's some notes to help you get started. In part 2, you're asked to determine the order of reaction. The rate law for our iodine clock reaction is equal to rate is equal to the rate constant times the concentration of I minus raised to the power of x and a concentration of persulfate raised to the power of y. X and y are the orders of reaction with respect to each reactant, and K is the rate constant. The first thing you should know is you should always use equation 8 to calculate the rate calculations. This is extremely important because if you don't use this concentration, you're going to end up with results that are going to be markedly off. For part B, after observing the reactions and getting the times, you'll calculate the rate of reaction using the concentration of thiosulfate. The times will change because you're looking at the change in the times will change because you're varying the amount of the concentrations of the other reagents. The concentration of thiosulfate will always remain the same, and this isn't intentional. Once you calculate those rates, you'll take the natural log of the rate and plot it against the concentration, the natural log of the concentration of the reagent of interest. This should give you, your data should fit to a linear regression, and the slope of that line will end up equaling x, or the rate of reaction with regards to iodine for this particular example. In part 4, you'll have to calculate the activation energy. The first thing you'll want to do is calculate the rate constant at the decreased temperature used in the experiment. Then you'll use this along with the rate constant at the lab temperature, which was about 21 degrees Celsius, and plug it into the two-point Arrhenius equation, which is shown here on the slide. You're solving for the activation energy here. Remember that R is equal to 8.314 joules per mole times Kelvin. This means that you want your temperatures in kelvins. You can do this. You can accomplish this by adding 273 to the Celsius temperature.